This is video 5 in the AC theory unit, and we're going to look at capacitance. So capacitance is a measure of the ability of a capacitor to store an electric charge when we put a voltage or a potential difference across the capacitor. And it's got the unit farads. Here's a diagram of a capacitor, and we're going to put that voltage on there, and it's going to put electrons on the plate. And it's going to be a build-up of electrons on that bottom plate that gives us the potential across the plate. There's three factors affecting the capacitance. The first one is the area of the plates, the distance between the plates, and the dielectric that's used. So if we increase the area, we'll increase the capacitance. If we increase the distance between the plates, we actually decrease the capacitance. If we put a different dielectric in there, so a vacuum is the worst dielectric. If we increase that by replacing it with air, paper, mica, we can increase the value of dielectric and increase the value of the capacitor. The time constant of a capacitor is an indication of how long it takes for the voltage on the capacitor to rise to maximum. So the time constant is C times R, the capacitance times the resistance. And that will give us the time in seconds for it to reach 63.2% of its maximum charge. And it's going to take 5 times that time to reach fully charged. So after 5 time constants, it's fully charged. The capacitor stores energy in the form of electrons on the plate, and we have a formula for that energy, which is half times C times the voltage squared. So the energy in joules is half times the capacitance times V squared. When we put a capacitor in an AC circuit, what that does is it knocks the current and the voltage out of phase by 90 degrees. Now, in a capacitor, the voltage takes time to reach maximum. So when we look at the phasor diagram, the voltage is lagging behind the current. So our reference is along the horizontal with a voltage, and the current leads by 90 degrees. And you can see that in the sine waveform, that the grey current line is starting at 0, but the voltage doesn't reach maximum until 90 degrees later. So the current is in front of the applied voltage by 90 degrees. A capacitor in an AC circuit causes capacitive reactance. We looked at inductive reactance, which was an inductor in an AC circuit. A capacitor also produces reactance, known as XC. And again, that's measured in ohms, and we use the formula XC is 1 divided by 2 pi FC, where XC is the capacitive reactance, F is the frequency, and C is the capacitance. Similar to the inductive reactance, the current is going to be proportional to 1 divided by XC. So if we increase XC, we'll decrease the current flowing. And if we decrease XC, we'll increase the current flowing. So the current is inversely proportional to the inductive reactance caused by the inductor. The variation of capacitive reactance with frequency. So if we look at the formula, it's 1 divided by 2 pi FC. So F is on the bottom of the formula. So if we increase the frequency, the capacitive reactance is going to decrease. And if we decrease the frequency, the capacitive reactance is going to increase. And so it's proportional to 1 divided by frequency. So capacitive reactance is inversely proportional to frequency. We can use capacitors in a number of different circuits. This is used for high frequency coupling in an AC circuit. And so what we've got there, we've got the capacitor before the resistor and the output to the circuit, and what it will do, it will allow a high frequency signal through, but it will block DC and low frequency signal. We can also use it to smooth in a DC rectified circuit, as we've seen in the DC power supplies circuit. So a capacitor connected across the load will try to smooth out the pulses of the DC. We can also use the capacitor for power factor improvement. So most industrial circuits are very inductive. They've got lots of coils, motors, transformers, things like that, that produce a bad power factor. We can put a capacitor into the circuit to balance out some of that inductiveness, and that will save the consumer money. We can also use a capacitor to reduce arcing, and the capacitor will absorb the arc and stop the arcing across contacts. It can also be used to suppress radio frequency, and again the capacitor can absorb the unwanted frequencies. There's must be a provision for charge and control of a capacitor, so any capacitor more than 0.5 microfarads must be provided with a discharge path, and you can read there the values of time for different voltages.